These are the notes for Standard 3.3. Today we'll be solving problems using Newton's first law. So, Newton's first law states that an object in motion will stay in motion unless acted upon by a net force. Additionally, an object at rest will stay at rest unless acted upon by a net force. So basically, what that means is for an object to change its velocity, it needs to have an unbalanced force acting on it. This is also called a net force. So if we look at a couple examples here, this shopping cart is being pushed to the right, and the push is larger than the force of friction, so there are unbalanced forces, so this shopping cart would accelerate to the right. In our second example, here we have a shopping cart being pushed with an equal amount of force to the force of friction, so here we have balanced forces, they're kind of canceling each other out, so this cart would either not move or it would continue moving at a constant velocity. Basically, we would say that it does not accelerate. So that could mean it's at rest, or it could be moving at a constant velocity. So here is how we solve problems using Newton's first law. If we take a look here, we have a 2 kilogram textbook sitting at rest on a table. We want to know what is the normal force that acts on the book. So as always, we're going to start with a force diagram. So here's our book. It's at rest on the table. There's just the force of gravity going down and a normal force from the table acting on the book going up. Since it's sitting at rest, those two forces are going to be balanced. They would only be unbalanced if it were accelerating. It's not, it's at rest, so those two forces are equal. And now that we know that, we can use that information along with the equations we learned in 3.2 to get what the normal force is. So we don't have an equation directly for normal force. It's part of the friction force equation, but there's no friction here. So we have to find normal force indirectly. So what we'll do is use the fact that normal force is just equal to the force of gravity, and we do have an equation for force of gravity, so that will let us find the normal force. So we'll start by finding the force of gravity by using our equation, Fg equals m times g. We can plug in our values, so it tells us in the problem mass is 2, and then g is just 9.8. So if we multiply them, we get that the force of gravity is 19.6 newtons. So then since we've already determined that these two have to be equal since it's not accelerating, that means the normal force is just 19.6 newtons. So that's the answer to that question. If we look at a slightly more complicated example, here we have a shopper pushing a 20 kilogram cart using 40 newtons of force. We know that they move at a constant velocity, and we want to find the coefficient of friction between the cart and the ground. So there's a couple things going on here, but as always, we're going to start with a force diagram. So if we look at our cart, it's getting pushed to the right. We have a normal force going to the right from the push. We have a friction force going back to the left. So normal force to the right from the person pushing it, friction force between the cart and the ground, and then we have the normal force of gravity going down and a normal force between the cart and the ground going up. So we know that the force of gravity and the normal force are going to be equal to one another because it's not accelerating in the vertical direction. This is usually going to be the case, that force of gravity is equal to normal force. Whenever we have horizontal motion, that's going to be true. In the x direction, or in the horizontal direction, here we know the push, so the normal force from the person pushing on the cart and the force of friction, we know that those will be equal because it tells us they move at a constant velocity. So those words right there, constant velocity, that's basically telling us that these two horizontal forces have to be equal to one another. Just to clean it up, we'll get rid of that cart. So we're just looking at this force diagram here for the object. So now, remember, we need to find the coefficient of friction. So we need to think, how can we get to coefficient of friction? And we have to remember, it's kind of hidden inside of our force of friction equation. So our force of friction equation is just mu, that's our coefficient of friction, times the normal force. So we need to find a couple things. If we just know what the normal, or if we know what the friction force is and we know what the normal force is, we'll be able to solve for this coefficient of friction. So the first step will be finding the friction force. That one's easy enough because it tells us they're pushing the cart using 40 newtons of force. So that means this force to the right from the push is just 40 newtons. And then since we've already determined this is moving at a constant velocity and these two forces are equal to one another, well, that means the friction force must also be 40 newtons. Then The second part is to get this normal force, because then we'll be able to solve for coefficient of friction. So to get that normal force, we don't have a way to find it directly, but we do know it's equal to the force of gravity, which we can find. So now we'll just do like we did in the last problem, use our force of gravity equation, Fg equals m times g, and plug in 20 kilogram cart times 9.8 gets us 196 newtons for a force of gravity. And then again, that's equal to the normal force going up because it's not accelerating in the vertical direction. So we know that normal force going up is 196 newtons. So now we have friction force, we have normal force, and we can solve for our coefficient of friction. So we can just plug our values in, and we get a coefficient of friction of 0.204. One thing to point out, or two things to point out. First up, coefficient of friction doesn't have units on it, so it's just 0.204. That's it, no units, it's just a number. Second thing, in this equation, normal force, notice how we have two normal forces based on how we say this. This could also be called like Fp for force of the push, or Fa for an applied force, or Fn because that's a normal force, the surface of the person's hand pushing on the surface of the cart. Any of those would be acceptable here, but in this equation, when we say normal force, that is always going to be this vertical one between the object and the ground. So it'll never be any horizontal one, it'll always be that vertical one. So this normal force here, the one we're talking about, is the one that is perpendicular to the force of friction. It'll never be one that's in the same direction as the force of friction.